Hello everyone, welcome to my presentation. I'm AKM Sarwar Inam, a third-year PhD student from Sensing Technologies Laboratory, Faculty of Science and Technology, Free University of Bozen-Bolzano, Italy. Today I'm going to present for the IEEE International Conference on Flexible Printable Sensors and Systems, that is FLEPS 2021. And my presentation topic is Flexible Screen Printed Nitrate Sensors with Copper Nanocluster, a comparative analysis on the effect of carbon nanotubes. So at first, the outline, I will talk about introduction and objective at first, then I will show the fabrication of the nitrate sensor, and then the optimization of copper electrodeposition, and later I will talk about the morphological characterization and surface area calculation, and finally the sensor performance and some conclusion with some future works. So we have developed this electrochemical sensor to detect nitrate. So what is nitrate? Nitrate is a polyatomic ion. Salts containing this ion are called nitrate. It can be found in all kind of food because it is used as an additive. So it is present mostly in meat products, and it is a common fertilizer. So it is available in leafy vegetable mostly. And also it is a contaminant, so there is a possibility to find it in beverage items. So why this nitrate is important to detect? Because it is a potential health hazard. It is an allergen and can form carcinogen, especially when the limit is exceeded. And the acceptable daily intake is 0.8 millimole per liter. So the aim of this research is to develop a novel low-cost flexible screen printed sensor and the fast detection of nitrate comparing to the conventional method, and also lowering the detection limit. Here the screen printed sensor we have developed is shown. Then I will demonstrate the comparative analysis with or without the presence of single wall carbon nanotube in the sensor. First one is the working electrode of copper silver sensor. Here copper is electrodeposited because copper works as a catalyst to detect nitrate. And the other one is the working electrode of copper single wall carbon nanotube silver sensor, where single wall carbon nanotube has been incorporated because CNT helps to increase the surface area of the electrode. And with the presence of analyte, when the linear sweep voltammetry is applied with the help of a potentiostat, then there will be a characteristic curve, nitrate reduction curve, which shows that the nitrate is reduced to nitrite in both the cases of these electrodes. Then the fabrication of the nitrate sensor. Here I will demonstrate the fabrication step by step. So at first, a semi-automatic screen printer is used to screen print the sensor with the silver ink, and half of the reference electrode is screen printed with the silver chloride ink. Then we can go directly with the copper electrodeposition on top of the working electrode using cyclic voltammetry. This is called the copper silver sensor. And on the other hand, we can go the spray deposition of carbon nanotube on top of the working electrode with the help of a spray coater. And later we can electrodeposit the copper on top of the CNT coated working electrode. And this is the optimization of copper electrodeposition. Here, the electrodeposition technique was used for this copper nanocluster formation. Electrodeposition is to produce the metallic coating, as for example here copper, and on a conductive material, that is silver electrode is the conductive material here, which should be immersed in a salt solution. We have used copper sulfate salt solution here. This electrodeposition can be performed with cyclic voltammetry by applying a potential range from 0 to -1 volt, and the copper is deposited especially in the -0.6 volt. In the next figure, we optimize the CV cycle. Here we have applied total 4 that means 1, 2, 4, and 6 CV cycle to electrodeposit copper, and each electrode was tried with 4 different concentrations. Those are 0, 0.1, 0.8, and 1.6 millimole. And after plotting the sensitivity against number of CV cycle, it is noticeable that the 2 CV cycle showed the highest sensitivity. Also on the right side, you can see the reduction peak current obtained from 1.6 millimole of nitrate. There is electrode with the 2 CV that also showed the 2 CV cycle of the copper deposition showed the highest current. So more than 2 CV cycle actually covered up all the CNT, and the surface area decreased, and as a consequence, the sensitivity also decreased. So this is the morphological characterization, and here in this slide, the left slide, the SEM images is from the copper silver sensor where 2 CV cycle was used. It is observable that the copper electrodeposition was not uniform all over the working electrode, and some silver flecks are also visible. On the other hand, from the right side of this SEM image, it can be seen that each single wall carbon nanotube is uniformly covered with the globular shaped copper nanocluster. And the average diameter of copper nanocluster are from 200 to 500 nanometer, which perfectly matched with the recent literature. Also from the image, it is visible that the surface area increased. And now the electrochemical calculation of active surface area. We have applied different scan rate ranging from 25 millivolt per second to 500 millivolt per second for both the sensor, and plotted square root of scan rate versus current. From the linear correlation, it is proved that in both cases there are diffusion control processes, and also the surface area has been measured with the help of Rendell-Sevcik equation. The result is plotted in this graph, and the surface area of copper silver electrode is 0.04 centimeters square. And after incorporating single wall carbon nanotube, the surface area of this copper CNT silver sensor is 0.08 centimeters square, which was a 95.5% increment. Now the sensor performance for this nitrate detection. In this slide, the linear sweep voltammetry was applied within the potential range between minus 0.1 to minus 1.4 volt with the help of a potentiostat. Total 8 concentration from blank to 6 millimole of nitrate were tried. In this figure, there are total 5 reduction peak are visible. First 2 are cuprous and cupric oxide reduction. And this is the one that is for nitrate reduction. The other 2 are actually for nitrite and ammonia peak, as this is a consecutive reaction. To get the calibration curve, the reduction peak current of nitrate were plotted against different concentration of nitrate for both the sensor, and the LOD was calculated and found 0.218 nanomole for this copper CNT silver sensor, which was lower than the copper silver sensor. The linear detection range was from 0.1 to 6 millimole for both sensor, and the coefficient of determination was higher, 99.75% compared to the normal copper silver sensor. Finally, we go for the mechanical stability test. Here, the bending test was done with the help of a customized bending setup, where the bending radius was 5 millimeter. We have experimented 500 and 1000 bending cycles, and from the result, the stability against the mechanical deformation has been proved. Though the standard deviation increased from 2.07 to 6.07 after 1000 bending cycle, which is still within the range. So this is because of the possibility of some permanent nano cracks in the electrode. To conclude, the fabrication and characterization of this copper CNT silver sensor was done, and we have developed a novel, flexible, low-cost, easy-to fabricate screen-printed sensor. And when comparing this copper silver sensor with this copper CNT silver sensor, you can easily see that the electroactive surface area is increased almost double after incorporating single carbon nanotube. The sensitivity is 1.5 times higher, and LOD, limit of detection, improved. That means it decreased to 0.218 nanomole. So there are some future works also left. Those are like the stability of the sensor, the selectivity of the sensor, and also the real water test. And result must be validated by a reliable analytical technique like HPLC. And that's all. Thank you for patience hearing.